Our next speaker has dedicated his life to creating artificial gravity in space. Still waiting to fly, but hopefully he'll persuade some people here and get that up as soon as possible. Joe Carroll. Thank you.
Good morning. Paul Davies' talk might be considered the view from 13 billion years. My perspective is much shorter. It's decades. But it's not humans to Mars in a decade. It's more humans on Mars for a decade or decades or maybe for good. And the questions that arise are quite different from the questions that all relate to the rocket equation, which determines the cost of getting to Mars. I think it may be relevant that the colonies in the New World, getting across the Atlantic a couple hundred years ago was a challenge. But staying alive once you got there was far more of a challenge, okay? And those are the questions that I'd like you to think about now. And to get a feel for this audience, how many would like to go to Mars? Okay, how many would like to go to Mars if you knew you couldn't come home? Okay, much smaller number. How many would like to go to Mars and have kids? Okay. How many would like to go to Mars and have kids if you knew that they couldn't move back home? Okay. Different questions, okay? Yeah, in fact, in an inversion of last night's discussion, maybe the way you get away from your kids is you can move back to Earth, but they can't. So, even something as simple as this, there are many unexpected questions, and I'd like to get you thinking about some of them. So let's see. Okay. Now, this is to me the most remarkable and remarkably convenient coincidence that I know of about our solar system. How many of you have ever seen this data which shows 5 planets having gravity levels, 4 other planets having gravity levels within 12% of Earth's? Okay. Or Mars and Mercury within about 1% of each other. Or the 6 largest moons in the solar system, the 4 Galilean moons plus Triton plus or Titan plus our moon, as being Earth's moon plus or minus 20%. Okay, yeah, one person here, okay? To me, this is something that tells us about our future in the solar system. Okay, the places that we can go that we don't have to adapt to other gravity levels are not particularly inviting. I mean, Venus, well, maybe the upper atmosphere, you could live there. But Neptune, Saturn, Uranus, not particularly attractive places to go. Okay, Mars, yeah, I mean, it's got the surface is all dry. It's smaller than the Earth, but the dry area is about equal to the land area of Earth. That's a significant thing, okay? And Mercury, may be a good source of materials. There's plenty of solar energy. It may be habitable near the poles. And if you don't like those 2, there are 6 other places that, if you can adapt to this gravity level, all become accessible from that point of view, okay? I really think this is significant. Now, there's another side to the story, and by the way, this graphic and this graphic, that's the key to my talk. If you remember those 2 and let them rearrange the furniture in your brain, I think you'll have the effect that I want to have on you, okay? We know every time astronauts spend more time in space, we find more problems, okay? It's not saying that they're not solvable, but we do have problems, and we have been looking for solutions for 50 years, and we don't like the solutions we've found so far very much. We are very familiar with this. We have data on 12 guys in the 60s spending 1 to 3 days at lunar gravity, and great, there was also a control case. There were 6 more guys in the Apollo command module, okay? But the differences between them, according to John Charles, who's the chief scientist of the human research program, he says that he can barely see data from the noise in the astrobiology monitoring from Apollo, and you can't tell how much of the difference that you might see was from 6 guys just floating in space and the other 12 running around in moon suits that weren't particularly, they were engineered in a hurry. They got a lot more exercise. So how much was the gravity and how much was the exercise difference? We really don't know. The most important part of this graphic is the question mark, okay? We really don't know what the effect is of partial gravity, okay? And I used to give talks related to this where the title had artificial gravity, but only a couple of years ago, I realized that the important word is partial. You can't test that on the ground. You can test hypergravity. You can put people in centrifuges, but you can't test hypogravity on the ground for more than a few seconds, okay? So what is the effect? Well, whoops. Okay. Questions for early partial gravity bioresearch. Can we stay healthy? That's the most basic question. Do rodents and primates reproduce normally in low gravity? In microgravity, they don't. Apparently, implantation of a fertilized egg does not occur normally. That's what I've heard. Can primates raised in low gravity adapt to Earth gravity? This is the question of, can your kids come back? Okay. I think it'd be better to answer that with other animals before we start doing it with human beings. What crops and ecosystems, a crop is not going to be just a crop. When Biosphere 2 was getting loaded up with its life forms, they brought trees in with root balls, and the root balls had ants. And my understanding is that the first year, the Biosphere crew, all lost weight, mostly because the ants ate about as much as they did. Okay? They intentionally did not bring insecticides. They did, after 1 year, import some predators for the ants. And by the way, what you grow, one of the other things about Biosphere is they did bring a coffee plant, but it turned out to be enough to provide each Biospherian a cup of coffee every other week. Okay? We may be one of the first generations in history who is so fortunate that we can take the reliable supply and low cost of food so much for granted that we can think about building cities for 1 million people and not think about how many square miles of farm area we need to feed those people, okay? It's going to be the South 40. You have a homestead and you're going to have a large area, even with intensive agriculture. The phrase astronaut farmer was the title of a movie, and the astronaut was named Farmer. It was multi-layer, but astronaut farmer those are 2 words that you're not used to hearing together, but that will be real. Okay. There are near-term issues that gravity, how much gravity should we use going to and from Mars? Do people want to pre-accommodate to Martian gravity on the way, or would you rather keep your muscles up to normal by Earth gravity on the way? What's the spin rate? These are all things we need because a lower spin rate requires a longer facility, and that requires more tether mass. It's not a big deal, but there are implications for this. And what countermeasures might you still need because partial gravity may not be enough? So I could go on for a long time, but one of the other questions is, where should you start partial gravity research? You can start it in LEO, in train with ISS or some other orbit, somewhere in deep space, same kind of spinning facility, or you can actually go to the moon or Mars. And I think realistically, if you want to stay a while, my friend Jim Logan, former flight physician at JSC, says you can visit the moon or Mars, but you can't live on them. You have to live in them for radiation protection. Now, Bob is somewhat skeptical of how much dose we can take of cosmic rays, et cetera, but we probably want some protection, okay? How many of you are familiar with underground gardens in Fresno? Okay, it is the place on Earth that may be most like a viable, architecturally interesting off-Earth settlement on the moon or Mars, okay? Anytime you're anywhere near Fresno, preferably in a hot summer afternoon, go visit it, okay? Call ahead because the tour schedule is kind of irregular, but it is a really interesting experience. Okay, undergroundgardens.com. It was done single-handedly by Baldassare Forestieri starting a little over 100 years ago. He bought some land in Fresno not knowing what the summers were like. And when it got hot, he remembered how comfortable it was digging as a laborer the Boston subway tunnels. And so he started digging. And he dug for the next 46 years. Okay. So my concept for a partial gravity research facility, the earliest versions of this are 30-plus years old. And they involved external tanks. And it was an asymmetrical dumbbell with a 7-to-3 mass ratio. And the idea is you get 2 for 1. You get Martian gravity at one end and lunar gravity at the other. Okay? And since then, it's evolved. There aren't any external tanks available now. Okay, 30 tons that could have been taken to orbit for free. A rotating facility can provide any desired gravity level, even full G or more, but the really interesting things are the partial gravity because you can't get that on the ground. Such a facility can study response of both humans and other biosystems, including crops, to the 2 partial gravity levels relevant to the 8 of the most interesting places in the solar system. And, you know, moon gravity level and Mars gravity level, even if you have no interest in those 2 bodies, they're relevant to 8 bodies, 6 others besides the moon and Mars, okay? And there are no other gravity levels comparable to those that are relevant to the solar system. And for a while, no matter how optimistic you are, we're probably stuck to this solar system for a while, okay? So the major unknown is allowable rotation rate. I'll talk about that a little bit more later. Now, this goes back to the 50s, okay, wonderful sales job. But a dumbbell allows a far larger radius and lower Coriolis effects with far lower total system mass. In addition, you can inherently get 2 gravity levels, whereas here it has to become a double donut with 2 different donut radii. You can also start with this plus a spent stage. You don't need the whole thing to do some early tests on Coriolis effects, spin rate effects, et cetera. And the real punchline, I think, is if you really have a business case for this, it's going to cost so much, you're going to have to sell this, really. Okay, because this is going to be so much cheaper, and it'll answer key questions. Once you ship the first element of this, you're locked into a certain diameter and spin rate. This one, you can send one up and do tests, and all you throw away is the cable if you decide that you need it longer or you want it shorter. Okay. Spin rate drives dumbbell length and design, and there's an ugly side to this, and that is the acceleration that you feel is spin rate squared times radius. And if you want to cut the spin rate in half, The radius has to be 4 times larger, not twice as large, okay? And we really don't know what spin rate is acceptable. There have been a lot of rotating room tests, okay? 3 days, they were in the room during the day but not at night, and then a smaller crew for 2 weeks. But rotating room tests, the rotation rate is, or axis is vertical. No matter which direction you walk, you get the same Coriolis effect, okay? In a rotating artificial gravity facility, the rotation axis is this way, and that seems like maybe not much of a difference. John Charles mentioned it to me as a difference, and the more I thought about it, the more it worried me, because in a rotating facility, if you walk in the sense of rotation, you get heavier. If you walk in the other direction, you get lighter, okay? If you walk along the axis, you get no change. And in fact, that's one of the reasons for having a long, thin facility. You line that up with the spin axis so that you can do most of your walking in directions that don't have a Coriolis effect, okay? But there are also effects, absolute rotation effects. When I'm rotating in a room, it's just a bias shift in my sensing, okay? If I turn, no matter where I am in the room or how fast I turn or how far I turn, it's just added to the room rotation. In an artificial gravity facility, if I'm standing facing this way and rotating this way, if I turn around, the sense rotation reverses, okay? So there are things we don't know, and we can test some of them on the ground but haven't, and others we really can't test on the ground. And those drive the length, okay? So we can design the modules, but we can't tell how long it's going to be until we do some on-orbit tests, okay? And it's reasonable that you might be able to get by with spin rates of several RPM. I doubt it, but it's possible. If it's short enough, you can go with rigid modules, okay? Like this, okay? Whatever this is, you make more copies, and that becomes this. If it gets long enough, that's too heavy, and so you go with inflated tubes that have some similarity to Bigelow modules, and I'll show you a better example of something close to that. You can make this longer, or if it gets really long, you do it just for part of it, so you can connect part of the modules, but the one that's furthest out, the Mars module, is connected by cables, and you have to get into a pressurized elevator to get from one to the other. And you do want to be able to go from one place to another, because some vehicles may only be able to rendezvous with the spin axis, okay? I think trapeze captures will end up being very attractive and turn out to be the preferred way of doing things, because it can save you 100 meters a second on the way to orbit and 120 meters a second on the way home by catching things in a slightly suborbital trajectory. So here's how you can start doing spin tests, spin sensitivity tests. My last slide is a video of 90 seconds of the mission film from Gemini-11. A friend of mine had somebody walk into his office in 1964-65 and say, we're running through the list of tasks that we have to resolve for Apollo on Gemini quicker than we expected for many of them, and we've got room to do interesting experiments. Could you do some kind of tether experiment? Well, from that day until they flew a spinning tether experiment was less than 1 year, okay? A manned flight experiment that was quite novel in its implications and had non-trivial safety implications, was conceived, developed, and launched and executed within, it's less than a year, and it may have been well under a year. I don't know. But the idea is you use the spent stage. In Gemini, it was an Agena that they had to rendezvous with. But in this case, you could use the spent stage from that launch, okay? And make this a ½ kilometer, spin up. You'd like to spin from this end, but you've got the thrusters at this end, so you spin up. But you do it with pulses when you're at the top going forward. And that ends up, if you let go of the tether when you're on top, all the energy you invest in spinning up ends up remaining here. So that the mass penalty of this experiment is basically the mass of the tether, and that could be tens of kilograms, under 1% of the mission mass. Okay. What module diameter and layout should we use? Okay. This is what we use in the space station. Okay. It's driven by decisions made by NASA to get DoD buy-in to part of the shuttle funding costs about 1970. Okay. It may or may not be the best solution now. Okay. 5.2 is the fairing diameter of the Falcon 9 and EELV heavies. 3.6 is the diameter of the Falcon stages, the Falcon 9 in heavy stages. I kind of like this because there's not as much opportunity to walk in directions that trigger weight changes. And by the way, your sensitivity to weight changes is fairly significant. When you get on an elevator and you start to move around as it accelerates or decelerates, you usually stumble. That weight change is about 5%. It's hard to make a spinning facility spin slow enough that your weight changes associated with walking, you know, with or counter rotation are less than that. So, you know, there is an argument for this. Okay. The other part of the system, I really would hope that the tests that we would do with this tell us that spin rates of 0.7 to 1 RPM are acceptable, because if so, then we can afford to use tubes like this. And by the way, when there isn't a BMW hanging from it, 2 people can lift this up. Okay. It's Vectran fiber and a polymer matrix, elastomeric polymeric matrix. If you replace that with quartz fiber and silicone, you can make it translucent and actually grow crops inside it when you're not using it as a tunnel. Okay, and there's some interesting things you can do. In fact, let me discuss that. Growing food in inflatable radial tunnels. If this is the kind of length that you need, you know, 0.5 kilometer to 1 kilometer for 0.7 to 1 RPM, that ends up being half or more of the total mass, total drag area, including the solar arrays that run the facility. Okay, and study that I was involved in 30 years ago looked at closed ecological life support systems. It was actually a one-day workshop that Dave Brin ran at California Space Institute. And one of the things that we were told very clearly was that if you try to provide the light by solar photovoltaics and, you know, the most efficient light sources you can find, not only is that a real driver of the system size, but the light efficiency isn't very good, and so you end up having a heat rejection problem. Now, we can do far better now than we could then, but I think that there's still advantages to using filtered sunlight if we can, okay? But one of the questions is, do you need light during the 36 minutes or so that you're up to 36 minutes that you're in the shade every hour and a half, okay? And there have been a few tests done in that, but they've not been well designed, okay? Some of them were 45 minutes on and off, and that's not the real cycle. How much thermal mass do we need for the brief night? How much will adequate micrometeoroid orbital debris protection weigh? And can farm automation experts make something like this work? And this is a real bizarre thing that I'd like you to think about. How many of you are have a current or association with or went to a land-grant college? Okay. Is that college involved in space? It's a rather surprising thing to me that Utah State, known for the small sat program, okay, Cal Poly, known for the P-pods and CubeSats, those are both Aggie schools, okay? And I asked Jordi Fuxuari from Cal Poly about that, and he said, well, Aggie schools usually have good ME departments, and that probably explains it. Well, turns out that to be a land-grant college, to get funded for that, you need an agriculture department and a mechanical engineering department. That's in the 1862 Land Grant College Act. what we need to do is walk across campus to the Aggie department and get them involved, because without making food, we're not going to stay off Earth very long. Okay? Everybody here, if you're going to live the rest of your life on Mars, you need at least 100 times your weight in dry food, either grown there or imported. Okay? I can believe that you can say a Mars base could depend on Earth for food. But by the time you get to something you want to call a settlement, you got to be growing most of your food. And by the time it's a colony, you got to be providing all your food and most of the other consumables. Okay. Conclusions. We've been going into orbit for 50 years, but we seem stuck. Okay. Every time we've tried to propose to go beyond Earth, we run into a financial roadblock when the program gets costed out. Let's look at it differently, okay? There are 3 gravity levels: Earth, Moon, Mars. They cover the 13 bodies of most interest, and the 8 partial gravity bodies, 2 levels, Mars and Moon, cover the 8 most interesting and accessible places. The other thing is, you know, the gas bags that have near 1 Earth gravity, those are high escape velocity. Those, you don't want to go there even if you can, because you won't be able to come back very readily. We can start with tumbling dumbbells tests, like the Gemini-11, to learn what spin rates are needed and adequate. And then 2 things not related to this, but I think really important, is settlements need local food production, recycling, and overall sustainability, even more than better rockets. Now, I don't know how many political liberals there are here, but sustainability tends to be a liberal word, but it is an absolute essential if you want to live somewhere beyond Earth. Okay? So sustainability, sustainability on and off Earth have more in common. Now let's think about solar arrays, okay? You say, oh, photovoltaics are photovoltaics. No. Silicon solar arrays sold in the ground cost a fraction of 1% as much as the best solar cells that are used commercially. Best not because they're the most expensive, but because they're most cost effective, despite being ridiculously expensive, okay? So power technologies, even within the field of solar arrays, are very different for terrestrial and space. Transportation technologies, rockets have not that much in common other than, you know, like sheet metal, with cars, ships, jet engines, airplanes, okay? Sustainability, there is a lot more in common between terrestrial needs and off-planet settlement needs. So make friends with the folks that think about sustainability, okay?
Gonna hate to leave this Agena. It's been pretty kind to us. Sure has.
After undocking, the command pilot pulled the tether taut. The purpose is to investigate modes of stabilizing a space vehicle during station keeping without using maneuvering fuel. At first, he had difficulty getting a taut line fully extended, and at one point told the ground that it was like skipping rope. Command pilot Conrad then put his spacecraft in a very slow spin of 40 degrees a minute. He made a complete revolution in 9 minutes. Later, at the request of the flight director, the spin rate was increased to 55 degrees a minute. Spacecraft and Agena again stabilized on the tether.
The tether is maintaining tension at all times. I'm impressed.
Station keeping in this mode became so uneventful that at one stage, the crew took time out for a bite to eat. After 2 revolutions, the tether was released by jettisoning the docking bar on the nose of the spacecraft. The tether floated erratically in space. The command pilot said it's wrapping around itself like a Christmas present. Goes 100 feet one way, then 100 feet the other way. Gemini-11 now separated from the Agena with a velocity change of 9 feet per second, and the last full day of the mission.
Okay, this presentation has about 10 backup slides, and the last one is a bibliography that has about 15 items related to the partial gravity, spinning facility designs, et cetera. I don't know what the plans are for making the presentations available, but I'd like to see them available to whoever wants them, okay? Are the presentations available for people to download electronically?
I think what you can do
Yeah.
is just email the slides to our webmaster right over there.
Okay.
And he can post them.
Okay, very good. So my time's up. Time for a question or two?
One question.
Okay. Jeff.
More of a comment than a question. On the question of what the facility tether length would be, another consideration is the fact that, of course, since you're in orbit, there's a tidal force gradient. So as you rotate, you will be modulating the gravity
and
level.
That is mostly a problem if you're multiple kilometers long. But
The longer you are,
the
more of an effect there is, but the slower the effect is.
Yeah.
Whereas the shorter you are, the faster the variability happens, but the less the magnitude of it. So it's an interesting additional consideration.
There's no length that gives you no undetectable artifacts, or no detectable artifacts. Anybody who wants to continue this discussion, I will be at the food court at noon. Join me for lunch. Okay.
Hey, Joe, go ahead and take one more question we're having. So, Doug?
Yeah.
So just a question of the cost, and are you suggesting that we do this first, that we delay either going to the moon or Mars before we do this?
That's really a money question more than anything else. And I envision this as something that could be done if Elon wants to do it as part of his qualification for the Falcon Heavy that he's so worried about right now. Okay, launching payloads that have a low replacement cost, the structures and the ham sandwiches and food and water tanks and all the stuff that you'd want should be much cheaper than a typical satellite payload. And so this is something you can do quickly if you choose to, because you think it's important. I think it's best done with as much commercial participation and funding as possible. And I can think of, I think multiple countries might be interested just to be part of crop growth experiments on the crops that are important for their culture and their country. Because 1% of what we are absolutely positively sure of about agriculture is probably wrong. But we don't know until we look at it in a new way. And so I think that this would be not only fun, but I think that fundable, okay, through untraditional sources. Monsanto might want to do it, okay? I'm not sure I'd want them to, but they may want to.
There's a delay. Can we do a Mars flyby before we do this? Is it necessary? Do we have to hold off?
I think you want to do this before you design the Mars flyby vehicle, because you want to decide how fast the Mars vehicle should spin in order that you don't have boneless chicken astronauts when you come back. Okay, I love the Gary Larson cartoons showing the boneless chicken ranch.
Thank you.
Okay.